Well, good morning, everybody. Sorry about that. I was waiting for anybody else to show up, and they're late. So, this is day 18. Beginning of the downward slope at the end of the semester. Today, we're going to talk about Chapter 7, Section 3, hyperbolic functions. Hyperbolic functions are pretty interesting animals in themselves. A hyperbolic equation looks like that, which is where it gets its name from. But we're looking at the functions are all based on e to the power u and e to the negative u, or some combination thereof with those guys. All right, so we're going to define all the trig functions with respect to the e values. For example, sinh, the sine, hyperbolic sine of x, is defined as e to the x minus e to the negative x over 2. This is pronounced sinh. The other one, cosh, is defined as e to the x plus e to the negative x over 2. So they're just opposites of each other. I thought you dropped. I thought you dropped. Oh, I'm sorry. And this is pronounced cosh. So these are the basic of the hyperbolic functions. And well, inside here for the students here, I have, and I'll put it online also, I have all these trig tables and graphs of the hyperbolic functions. So, for example, here's the function for e. That's e to the power x divided by 2. And here's the e to the negative x divided by 2. So the inverse sign is just on the insides of those. Likewise here, this is negative e, so this is why the sign is e to the x minus e to the negative x over 2. This one's e to the x plus e to the negative x. So the e to the negative x is like this, e to the x is like this, and the cosh is on the insides of those. And then the rest of the trig functions can be derived similarly from there. Cotangent, hyperbolic cotangents are those. So that means the tangent, which is the reciprocal one, is on the inside with the asymptotes, the horizontal asymptotes at 1, -1. Sech, with it, which is the 1 over cosine, hyperbolic cosh. Remember, that one is based on those e values, and here's the cosh. So it's just the reciprocal of that, but it can never be negative. And then likewise with the cosecant hyperbolic. This is 1 over sin h, which is, again, the e is there, the negative e is there, so it's just a reciprocal of those. And here are the functions for the hyperbolic tangent. The cotangent is sine of a cosine. This is cosine of a sine, hyperbolics. 1 over cosine sec, and then cosecant hyperbolic is 1 over sine. So, I mean, we use the same algebraic manipulations for those. And it's just, it makes it much easier to deal with. So we have all these. I'll for you guys online. I'll send it to you. So, for example, we have these. Let's look at a double angle of here of the hyperbolic sine times hyperbolic cosine. So sine is ex minus e negative x over 2. This one's ex plus e negative x over 2. The 2 cancels, so we just have a 2 on the bottom. And we have e to the x makes e squared x. The difference of 2 squares, the middle terms cancel, so we have minus e to the negative 2x. And that, since it's minus, this is the hyperbolic sine of 2x, since that's our u. All right, so that's what we'll be dealing with in this half of the course. And recall from calculus or from trigonometry that the trig functions can be used to represent circles, same as a unit circle was represented by x squared plus y squared equals 1. Is x squared plus y squared equals 1. We could do this with trig functions. We have cosine squared x plus sine squared x equals 1. All right, so we can look at doing it that way. So we can relate to the algebraic aspect using the trig functions. Now, how does all this fit into with hyperbolics? So if we did hyperbolic cosine squared of u, whatever that u is going to be, minus sine hyperbolic squared, that equals 1. And this is where they get their name from, because if we were to graph this, we'd have a function looking similar to that. All right, so our points now here, in this one, our points are cosine x, or cosine u, sine u. Here we have cosine hyperbolic u, sine hyperbolic u. Each point in our respective circles. The application of hyperbolic functions used in a lot in engineering and sciences. For example, the cosine, the cosh, is used if you had 2 power cables from the same height and they droop. If you look at the graph of the hyperbolic cosine, as long as the points are the same, we're dealing with the droopy line. And that's where the hyperbolic cosine will be used. The inverse of it is going to define an arch or an upside down U. Um, in oceanography, the hyperbolic tangent defines the velocity of waves over a distance with constant depth. Again, the consistency is pretty important, like we did with the cable, the cosine, hyperbolic cosine. In order to use it to define two as a droopy curve, we have to have the same height, the same altitude in both ends, as likewise with the inverse. So the waves themselves, if you look at waves, they are repeating themselves always. And if we look at the hyperbolic tangent, there, this is the wave function. Because it looks, this is the negative of it, but you would look at waves like this. As long as they're coming from the same, have the same depth. The inverse of the hyperbolic tangent used by Einstein in his theory of relativity. To discuss the sums of velocities. Because remember, since the hyperbolic tangent is the wave function, the inverse hyperbolic tangent looks like this with horizontal asymptotes at 1 and -1. There's the x-axis. This is the y-axis. So that's just a heads up on what this is used for. And we can find a lot more if you want. So first thing, let's look at derivatives of these things. And integrals of hyperbolic functions. So let's say our function was the hyperbolic sine, sinh. We have to relate it, and that's where it helps when we relate it back to our e functions, because then you would simply be taking the derivative with respect to the e values, f of u. So the derivative of the hyperbolic sine of u with respect to x is the derivative of that function. So since 2 is a constant, it stays on the bottom. We just have to take derivatives of these. So we have the derivative of u, eu is eu, times the derivative of the exponent minus e negative u times the derivative on the top, which will make it negative du dx. So these two cancel, make it a positive. If it was just x if it was just e to the x plus e negative x over 2, then what we would define there would be the hyperbolic cosine of u du dx, which is the same. Again, it's the same. The derivative of sine for us before this was the cosine. So now it's going to be the same thing. It's hyperbolic sine is hyperbolic cosine. Let's look at our function f of u equals cosecant hyperbolic with u. So the derivative. So the derivative of hyperbolic cosecant with respect to x. Cosecant is 1 over sine. So we take the quotient rule here. We have 1. The derivative of 1 is 0. Derivative of sine is cosine hyperbolic of u. Since it's quotient, we subtract. So this becomes hyperbolic sine times 0 is 0 minus cosine h of 0 times 1 over sine hyperbolic squared of u. So we know the function is going to be negative. So we have cos of u sine h of u times 1 over sine h of u times du dx's. Those are all with respect to u. So negative cosine over sine is cotangent. 1 over sine is cosecant h over u du dx. So there's the derivative. Again, and other formulas will be derived the same way. Once we get either put them into terms of the e functions, or we put them in sine and cosine, since we have those. Let's look at an example here. Here you go. I have these for you. I have these graphs and everything for you. So example 1. Let's do example 1. Example 1 says, find the derivatives of these 4 functions. Okay, so example 1, A. The derivative with respect to t of hyperbolic tangent radical 1 plus t squared. Now, since we have our, I gave you this sheet, and you also have the in the cheat sheet I gave you at the beginning of the semester. So we have the derivatives of our trig functions, our hyperbolic trig functions. So the derivative of tangent is secant squared, secant hyperbolic secant squared. So we get secant hyperbolic squared of our u, which is square root of 1 plus t squared, times the derivative of our function 1 plus t squared dt. Taking the derivative of this, so we have square root of 1 plus t squared. That becomes 1 plus t squared to the 1/2 power. Take the derivative of it. So you get 1/2 1 plus t squared to the power negative 1/2. Take the derivative of the inside, which is 2t. The 2's cancel. So it becomes t over radical 1 plus t squared. So our derivative of tangent hyperbolic is t radical 1 plus t squared times secant h squared 1 plus t squared. Right. The only thing changed is the formula we use. I mean, the other thing, formula, it's just the values we have. We do the same thing the same way. Okay, let's look at B. B is asking for the integral, the open integral of the cotangent hyperbolic of 5x dx. So the integral of the cotangent hyperbolic 5x with respect to x. Cotangent is cosine over sine. Actually, we could look at this. We could do the long way would be doing it the vectors of the quotient way, but we can look at this as seeing of u du. If u equals sine hyperbolic 5 sine x, the derivative of that is cosine hyperbolic of 5x. So what we have here is du over u. And with the 5 inside there, we need to have a coefficient of 5 here because the derivative of the inside is 5. So it means we have to put a 1/5 out in front. So the integral of du over u is ln, the absolute value of u, plus c, because it's an open integral. So we have 1/5 ln of the hyperbolic of 5x of sine, the absolute value of it, plus c. There's the open integral. Now let's look at c. The definite integral of hyperbolic sine squared. So c. The from 0 to 1 hyperbolic sine squared of x dx. Sine squared Let's look at this whole, where is that? Yeah. In our tables, so we have sine squared is here, so we can use that function, the double hyperbolic. So it's going to be cos of 2x minus 1 over 2. Yeah, I use my table just to convert that. It's over a constant, so take that outside. So I'll just have to worry about cos of 2x minus 1 dx. I could do these in parts. Cos 2x dx minus 1 dx. The integral of cosine 2x is sine hyperbolic 2x over 2 from 0 to 1 minus integral of 1 dx is x from 0 to 1. We have sine hyperbolic 2 times 1 is 2 over 2 minus sine hyperbolic of 0 over 2 minus 1 minus 0. So distribute those in there. I get sine hyperbolic of 2 over 4. That goes to 0. And this is 1, so it's minus 1 over 2. And that's as far as I can take it. Unless I have a calculator, I put in a calculator and it'll give me the answer. All right. Then let's look at D. The closed integral from 0 to ln 2 of 4 e to the x hyperbolic sine x dx. Since I have an ex there, let's convert this one to the e. Remember we said sine hyperbolic x was e to the x minus e to the negative x over 2. So we can just put that in there. Especially since our bounds are natural logs. So it's e to the x minus e to the negative x over 2 dx. The 2 and the 4 cancel. So we can have 2ex distribute through there. So we have 2ex times ex is 2e to the power 2x minus 2 ex minus x is x to the 0, which is 1 dx. So the integral of 2 e to x is, this is eu du. So that the integral of that is just e to the power 2x. The integral of 2 is 2x from 0 to ln2. So we have e to the 2 times ln2 minus e to 2 times 0, 2 ln2 minus 2 times 0. So e to the power 2 ln2, that's simply as e ln squared, that's b ln 4. It'll just be 4, because this becomes ln2 squared, so it's ln 4. E to the ln 4 is just 4, minus e to the 0 is 1. E2 ln this ln 4, because this is the exponent. So with 4 minus 1 is 3. And that's the number. Put it in the calculator, you got it. So again, it's just all algebraic from there. It's just not much has changed. Finding the derivatives of hyperbolic sines, hyperbolic functions, I should say. The problem is, do we keep it as hyperbolic functions or do we convert it to the e's? It all depends on what your bounds are. So there we looked at derivatives and integrals of hyperbolic functions. So now let's look at the inverse functions. How do we know we have inverse functions? I have inverse functions exist if you have a continuous function that's one-to-one. So out of our functions, we know that from our chart, let me get that copy of that chart from our graphs. So we see this the hyperbolic sine, that's one-to-one. However, the cosh is not, because it fails the function, the one-to-one test, the horizontal line test. So we have to use for the cosh, we have to have x is greater than or equal to 0. Same thing with the secant, hyperbolic secant. In order for us to take an inverse of that, we have to take the x's only from x being greater than 0. The rest of them works. Since they're one-to-one, we can find the inverses of them. So this is how it would look. Y equals the inverse of the hyperbolic sine and the cosine and the rest of the functions there. Actually, I think also in your sheets, I think I gave it to you. Yeah, there it is. The inverse hyperbolic functions. For the sine, you have the sine and the hyperbolic sine. It's flipped around the axis y equals x. You have the cosine from 0 being going to infinity, and we have the inverse function. The secant, remember, that is only from, because it was repeating itself. So we only took it from 0 to infinity, flip that across the y equals x axis. There's the inverse secant, hyperbolic. And tangent, same thing there. it's 1-to-1, so we take, and all these other ones. All right, so we know that we can take, and we know what the graphs look like. So let's see an example here. Oh, let's do the examples first. So since we have inverse functions, let's look at derivatives and integrals of inverse hyperbolic functions. And let me see here. And on the last page, you have those formulas already. So the derivative of the inverse of sine, hyperbolic sine, is that. The integrals, if we can get the integral into that form, we can translate it back to sine our trig functions inverses. So our next step is now try to make them fit those categories. Where's my example sheet? There it is. Example 2. Show that if u is a differential function of x whose value is greater than 1, then inverse cosine equals this. So what it's asking us is prove that this exists. Equals 1 over radical u squared over 1 du dx. All right, so our function is the inverse cosine. We know from calculus 1 that the composite function, or the derivative of the inverse, is 1 over the derivative times a compounded function of the inverse. That's a property, that's an identity theorem from calculus 1. So what we have to do is make our function fit in this, our derivative, and we have to go there. What's that? There. This, you have this on your sheet. So this is example 2. So what we have to do is we have to try to make it fit into this formula. But we're saying here the derivative where's that? Okay. So we're saying if we make our u value the derivative of u, because we're looking for the inverse, then our derivative is the sine function, and we'll make u the inverse function, which is the cosine. So we'll do 1. F prime is hyperbolic sine of the inverse, which is the cosh inverse with respect to u. Is it u? Yeah. With respect to x, because it's got to be x inside there. And sine of u, is equal to, where's my charts? Okay. Well, we said earlier, with respect to the x squared plus y squared equals 1. For the hyperbolic functions, it was cosine hyperbolic squared minus sine hyperbolic squared equals 1. Because what we're looking for is this: since we have sine and cosine, what we need, if we had cosh inverse of x, then we know that would equal x. If the function and its inverse, then it equals x. So since we have sine cosine, we have to make sine into cosine. So that would equal negative sine x is equal to 1 minus cosh squared x. Change the signs. So we have sine squared x equals cosh squared x minus 1. Square root both sides. Is equal to the square root of cosh. So that can go into there now. And this is my, wherever I see an x in there. So that makes our new function 1 over the square root of cosh squared x, and the x is this, cosh inverse of x minus 1. That's that. And because of this, since it's cosh is squared, then it means cosine x is squared. So this becomes x squared minus 1. Which is what we're looking for, x u squared minus 1. So there you have it. 1 over square root of x squared minus 1. Yeah, well, this is u, but if we just did u's then we'd have to have the du dx on the other side. But I did all these with respect to x. That one is not a fun one. Let's do that. Okay, in example 3, let's look at the integrals of these. Two radical 3 plus 4x squared dx. Yes. It said evaluate. So which one? We're doing integrals. So I got to use one of these. Or looking integrals go to derivatives. So we're going to see how they relate. So what this looks like out of these, since we have numbers in both of those, we have to have one that's an A, it's a plus. So we have one in A, yeah, so we'll have, this is the one we'll have to try to use. That's a U minus A squared minus. So the only one we can try to use is this top one. And that's going to be replaced with the sine function. So what we have is du square root of some number squared, some function squared, and that equals the inverse hyperbolic of u over a plus c. So this one we're saying is a, but it's supposed to be squared. A is 3. But it's supposed to be squared, so it's a square root of 3. But if we square a, then we get 3. U squared is 2x squared. So a squared equals 3. So a is just radical 3. So that means u is 2x. That means du is 2. Our du is 2. A squared is 3. And u squared is 2 radicals. Yeah, so it fits there. So that means this integral can become inverse hyperbolic of sine of u, which is 2x, over a, which is radical 3. From 0 to 1. inverse hyperbolic sine of 2 over radical 3 minus hyperbolic inverse of 0. Sine inverse of hyperbolic of 0 is 0. So we're looking at hyperbolic inverse of 2 over radical 3, whatever that value is. So you see how we did that one? Is we had the original question. We're taking the integral of that. So we have to try to match it with one of these 5 already set. Since that was something plus something, it's either going to be that one or this one, number 5. It can't be number 5 because there's nothing out in front of the radical. So we're going to try to make it fit that. So that's what I was trying to do there is this had to be a squared and this is u squared. And that's it for hyperbolics. So basically what a lot of it is just plugging it in and or try to find which one fits.